So in this question, we're told that a child drops a ball and the ball hits the ground and bounces. We have figure 14, which shows the velocity time graph for the ball when the ball is dropped until when the ball reaches the top of its first bounce. And then in this case, air resistance has been ignored, so we don't have to take that into account here. We then have figure 14, so we've got velocity on the y-axis, time increasing on the x-axis, and then the motion of the ball, so between A and B, B and C, and then C and D. We're then asked to describe the motion of the ball between points A and B on figure 14. So as we can see here, between A and B there is a straight line, increasing straight line with a constant gradient, and we can use this to work out what exactly is happening to the motion of the ball. So the gradient of a velocity time graph is going to be the acceleration of the ball. So the m, which is the gradient, is equal to the acceleration. And we know this, if we didn't know this already, we could work this out because we have the gradient of a graph is equal to the change in the y-axis over the change in the x-axis. And the y-axis is velocity, which is measured in meters per second. So if we work with the units, that's going to be a unit in meters per second. And we're dividing it by the x-axis, which is time in seconds. So the units there are the second. And that's going to give us a gradient which has units of meters per second squared, which is the unit for acceleration. So we can see here that between A and B there's a straight line, which means the acceleration is going to be the same no matter where you are between A and B. So that means we've got this constant acceleration. And the way that we described this constant increase in velocity is going to be with the term uniform acceleration. So just by stating that there's a uniform acceleration due to this straight line, and this line, the gradient of the line is the acceleration of the ball, we're going to get both marks here for simply stating the words uniform acceleration. We'd also gain them for saying there's a constant or steady acceleration, or that velocity is increasing at a constant rate, but this is the best way to go about getting both of the marks with not too much working out. And here we're being asked what direction is the ball moving between points C and D on figure 14. So to go about doing this, I'm going to have to work out in which direction velocity is positive and which direction it's negative. So we need to work out, as the C to D portion of the gradient has a negative velocity, so it's below this x-axis, we need to work out whether the ball has a negative velocity when it's falling downwards or if it's going upwards. So we're told in the question that the ball is dropped. So if the ball is at some point away from the floor and it's dropped downwards, and then it will bounce back up. So it firstly is travelling downwards. So in the portion between the graph A and B, this ball is going to be on its descent to the floor. It's being dropped. And then the point when it hits the floor, it's going to have a velocity of 0. And then it's going to come upwards with an initial velocity here between C and D. So when it's going downwards, that's this portion of the graph between A and B, and it has a positive velocity. So the downwards direction of the ball has a positive velocity. And then when it's going upwards, it's going to obviously have the opposite. We can see this as the velocity is negative between the C and D portion of the graph. So the question is asking what direction is the ball moving between points C and D, and then we've seen on the little diagram here that it's going to be coming back up from the ground, so the answer is going to be upwards. Here we're told the ball and the earth form a system, and we're asked what's meant by a system and ticks one of the below boxes. So firstly, we have the option a group of objects that interact, and the ball and the earth do interact. These are two objects that are going to be interacting in this reaction. And then we have objects with big differences in mass. They do have a big difference in mass. However, this isn't a required criteria for them to be in a system together. We finally have objects with gravitational potential energy. And that could be a component of the system. A system could involve energy transfers and that kind of thing. But this isn't the defining feature of a system. The defining feature of a system is that we have a group of objects that are going to be interacting together. Now, this could be through energy stores, through that kind of thing, through the transfer of energy. Or it could be in different ways. There are lots of different ways groups of objects can interact. And this is the main thing that defines them as a system. And the Earth and the ball are going to be a system in this instance. Now we're asked, when the ball hits the ground, energy is transferred from the ball to the Earth. And we're asked to explain how the data in figure 14 shows this energy transfer. So initially here I've realised that this question's worth 4 marks, and it's asked us to explain how the data in figure 14 shows this energy transfer. So it's looking for a bit more information, a bit more detail, and 4 key explained points here. So, first of all, I'm just going to work out where the energy is transferred in this interaction. So, when the ball's held above the ground initially, it's going to have energy all stored in its gravitational potential store. It's not moving, so it's not got any kinetic energy, and it's being suspended above the surface of the Earth, so all of its energy is going to be in this GPE store. As soon as it's released, this gravitational potential energy is converted into its kinetic energy. As it descends towards the Earth, it's going to speed up as it falls. So this gravitational potential is converted into kinetic energy, and then as soon as it hits the surface of the Earth, it's going to have a GPE of 0 because it's no longer suspended above the Earth, but it's going to have a greater kinetic energy because this energy has been converted. However, then, energy is going to be transferred from the ball to the Earth in this part of the interaction. So then the ball's going to bounce up. However, this time it's going to have less kinetic energy due to this loss in kinetic energy to the Earth. And that means that it's not going to have the same GPE when it reaches the highest point in its bounce. So that's going to link in nicely to the first part of the answer. As we can see using the graph here, we have the magnitude of the velocity of the ball just before its first bounce. So here that's going to be 7. Just before it hits the ground, its velocity has a magnitude of 7. And then we have the magnitude of the velocity directly after the bounce. It's going to be -5, so it has a magnitude of 5 meters per second. So as we can see, it's gone from the original 7 down to 5 meters per second. So the velocity just after the bounce is less than just before the bounce. Now that's because of this loss, this conversion of energy and some being transferred to the Earth. So that means that if it's got less kinetic energy afterwards, the height at the top of the bounce is also going to be less than the height from which it was dropped. So either of these 2 points are what we need to say to get the first mark. They're going to basically mean the same thing, just saying them in different ways. So we're going to have to write one of these down in order to gain that first mark. We're then going to go on and explain in a bit more detail what's happened. So because this velocity is less after than before the bounce, the ball must have lost energy. It's lost kinetic energy, so has a reduced gravitational potential energy after the bounce. And these 2 points here are going to get us those second 2 marks. So that the ball has lost energy will get us 1 mark. And then referencing this loss of kinetic energy or this reduced end gravitational potential energy will get us the 3rd mark. And then finally, to get the last mark here, we're going to link back to the previous question. So we know that the ball and the Earth are a system. So in order to explain this a bit further, we're going to say that the total energy of the ball and the Earth is going to be constant. So this energy is conserved between the two. And so just by going through this question in that logical order, we've been able to outline each mark point as we've gone and made sure we haven't missed any key information out. And explaining the question has been really important here as the command word in the question. We've had to give a little bit more detail and develop our answer a bit more. So in this question, we're told that a student carried out an investigation to determine the spring constant of a spring, and then we have table 4, which gives us the data obtained by the student. So in the left-hand column, we have the force in newtons, which from this kind of spring constant experiment that we've probably done before at GCSE, we're going to realise that this force is going to be the force applied to the spring. And then the extension of the spring, which is measured in centimetres in the right-hand column, is going to be how much the spring has extended from its equilibrium, its rest position, under the force in the left-hand column. So we're asked to describe a method the student could use to obtain the data given in Table 4. And we're told that our answer should include any cause of inaccuracy in the data, and it may include a labelled diagram. Now, obviously, I'm noticing here that this question is worth 6 marks, so it's going to be requiring quite a detailed explanation and development of the points and a good logical method with these inaccuracies brought up and shown in our answer. So, here we can effectively split our answer up into 2 main parts. So I'm going to start by focusing on the method itself, and then go on to this comment of this accuracy and inaccuracy elements at the end of my answer. So if here I begin by thinking about what I'm going to need in terms of apparatus, I always think that's a good place to start with kind of big mark experimental questions like this. So I'm obviously going to need the spring, and I'm going to be needing something to suspend this spring in order to allow for the extension that we see in the table. So I need to hold this spring up, and I could do this by using a clamp stand and clamping the spring above the ground on this clamp with a clamp on the clamp stand. So in order to measure this extension, I'm then going to need some kind of measuring implement. And in this case, we can see in the table that I'm working with values up to 20 centimetres. So a metre ruler would work quite well here. That would be quite an appropriate piece of apparatus to choose for this experiment. And then in order to ensure that the measurements here are going to be accurate, I'm going to clamp it in place using a second clamp, so clamping the ruler in place. And then we'll talk about how inaccuracies might come about if this isn't done properly a bit later on in the question, when I am talking through the inaccuracies in the data. I'm also going to be needing some 2 Newton weights to hang from the spring here, so we can see that the force applied goes from 0 to 2 to 4 and is going up in 2 Newton increments. So I'm going to be needing 2 Newton weights to hang from the spring, which is going to cause the extension present in the table. So once I've got this kind of diagram all set up, I can explain how I'm going to use this to go about completing the experiment with a clearer method. So once setting up the apparatus in the diagram, I can record the metre ruler reading that's level with the bottom of the spring. So this is going to be basically the equilibrium length and where we're going to take our measures of extension from. So I can then hang a 2 Newton weight from it and record the new position of the bottom of the spring, calculating the extension, so the difference between the original measurement and now this measurement. And I can then do this for every next multiple of 2 newtons, so adding a 2 Newton weight each time until I get up to this final value in the table of 10 newtons. And then I'm going to measure the extension from the initial position each time, so doing that subtraction, and that's going to give me the extensions in the right hand column. So as we can see, when there's a force of 0 newtons, there's obviously going to be an extension of 0 centimetres, because that is the position that we're calculating this extension from. So this method here that I've outlined is going to obtain all of the data in the table, so I've basically answered the first part of this question in that clear, logical way. now I'm going to move on to any possible inaccuracies. So these will commonly arise relating to values found for the extension of the spring. So maybe here, back to the idea of the ruler being clamped, if it wasn't clamped vertically, so if there was an angle in the ruler, that would affect the measurements for extension. Or maybe if it was held instead of clamped, so this is going to really cause some greater inaccuracies because the error in holding the ruler instead of clamping it is going to be much greater. Similarly here, the position of the bottom of the spring could easily be misjudged, causing a difference in the extension readings. Or it could be incorrect due to a kind of parallax error, so not reading it from the same level each time. So all of these points would definitely introduce inaccuracies into the experiment, so it's good to mention a couple in the answer to get those 6 marks. So overall, here we've explained the method in a really logical, step-by-step way using that detailed diagram at the start in order to aid in this explanation. And then we've gone on to add to our answer by including this section about the causes of the inaccuracies in the data here. So now in this part of the question, we're told that the student measured the extension for 5 different forces rather than just measuring the extension for one force. And we're asked to suggest why. This is just going to be worth 1 mark here. So we can just give a brief suggestion as to why we've conducted these sorts of repeats of measuring the extension for different forces applied. Now, one main reason for doing this may be in order to find any anomalies within the results, so we can discard them and come up with a more accurate value for the spring constant, perhaps by using an average of the reliable results that haven't been discarded as anomalies. So to get the mark here, I'm just going to write down that by doing these for different forces, it's going to help us to identify any anomalous results that we may have obtained, and then we can deal with these accordingly to come to a more accurate answer. So here we have figure 15, which shows some of the data which has been obtained by the student. So here on the y-axis we have the extension, which is measured in centimetres, and then on the x-axis we're going to have the force, which is in newtons. So then we're asked to complete figure 15 by plotting the missing data from table 4, and we're asked to draw the line of best fit. And then table 4 is repeated below to help us answer the question. So obviously here we can see that we have extension on the y-axis, and then extension is in this column of the graph. So this column of the graph is going to be plotted on the y-axis. And then we have force on the x-axis. So this column is going to be plotted on the x-axis. So for the first point, we have 0.00, and we can see that's already plotted here. Now if we move on, we have 0.2 on the x-axis and 3.5 on the y-axis. Now that point isn't plotted on the graph. So if we go to 2 on the x-axis, and if this scale goes up to 5 here, each increment of 2 small squares is going to be a measure of 1. So I could plot that on here. So these 2 small squares, we have 1. Here we have 2, 3, and so forth. So if we have the point 2, 3.5, we go along to 2 and up to where 3.5 is, which is this point here. We then have the point 4.8, which is plotted on the graph, the point 6, 12.5, also plotted, and now the point 8.16, which is missing from the graph. So if we go along to 8 on the x-axis and up to 16 on the y-axis, we get to the point here. And then finally, we have the point 10.20, which is plotted on the graph here. So now if we're asked to draw a line of best fit, we're going to basically try and draw a line through all of these points. So if I go from the starting point all the way up to the ending point, and then straighten my line, try and get it as close to all of the points as possible. And that would get us both the marks for plotting the final results and drawing on the line of best fit. It doesn't have to go through all of the points, but it just has to make sure that there's an even number above and below the line and they all sit very closely to this line. And here we're asked to write down the equation that links extension, force and the spring constant. So for questions like these, I always find it helpful to basically go through and write out the symbols for each of the variables. So we have extension, which is going to be delta L in this case. Force is going to be a capital F, and then the spring constant is going to be a K. So now these symbols might be looking quite familiar, and a way of arranging these might be coming to mind. So the way that I like to remember this equation is with the word folk. So if I write it like this, the O in lowercase, so we know that it's not part of the equation, and I have F is equal to basically LK. And that is basically the equation here, not the exact form that we're going to write it in, but it's pretty much how we're going to work with it. So I have here that the force is going to be equal to the spring constant, so K. And then we're going to multiply that spring constant by L here, which in fact should be delta L. So that's going to be the extension. So the equation is the force is equal to the spring constant multiplied by the extension, or F equals K delta L in its more common form. So here I'm asked to calculate the spring constant of the spring that the student used and to give my answer in newtons per metre. This is important to remember that I need to give my answer in this form, so I'm just going to jot down the units next to it just so they stand out and I make sure to remember to do any conversions that might be necessary. So this question is worth 4 marks, so it's going to be important to do some rearranging and working with the equation in this question and then linking back to these units and doing any conversions necessary. So I'm going to start off here with the equation that we had in the previous question. So we worked out that F, the force, is equal to the K, spring constant, multiplied by delta L, which is the extension. Sometimes delta L might just be written as E, but either way, that's going to work just fine. So now I can basically substitute in my values from the previous question. Now if I take any of the values, this is going to work because we have a straight line of best fit. But on a graph of force against extension, the gradient of that graph is going to be the change in y over the change in x. So that's going to be force over delta L. And then if we look back to this formula, when we divide both sides by delta L, we're going to be left with K is equal to force over delta L. So the gradient of a force extension graph is just going to be equal to the spring constant. So in this case, I'm working out the gradient of the force extension graph that we were working with before, and then that's going to give us the spring constant of the spring that graph is representing. So in that case, I'm going to take the change in force throughout the whole experiment. So the greatest force is going to be that 10 newtons that was applied. So we have the 10 newtons is equal to K multiplied by the extension that was created with that 10 newtons, which was going to be 20 centimetres. Now I'm really noticing here that we have this unit of centimetres, which doesn't quite sit right because we want our answer in newtons per metre. So in this case, I'm going to convert 20 centimetres into metres, and I'm going to do that by multiplying by 10 to the minus 3, or dividing by 1,000, whichever way you want to think about that. And that's going to give me 0.20 metres. So now I have that 10 newtons is equal to 0.20 meters times k. So if we divide both sides by 0.2 meters, we have 10 newtons divided by 0.20 meters. And if we put that into our calculators, that's going to give us a value of k of 50. So then I can just check the units here. We have newtons divided by meters, so that's going to be newtons per meter, which is, of course, the unit that we're looking for this question. So our conversions have worked, and the answer for the spring constant is going to be 50. So then the marks here are distributed like so. So firstly, for converting the centimetres into metres, and then substituting our values into the equation, doing the division to find k, and then calculating the correct value of k, which is 50. Now we're told that Hooke's law states that the extension of an elastic object is directly proportional to the force applied, provided the limit of proportionality is not exceeded. We're told that the student concluded that over the range of forces used, the spring obeyed Hooke's law. And we're asked to explain how the data supports the student's conclusion. And then this question is going to be worth 2 marks here. So we're just going to state our point and then go a little bit further into it to give a bit more detail into the explanation. So the keywords that I'm focusing on here are the fact that for an object to obey Hooke's law, the graph of force against extension is going to be directly proportional. Now, directly proportional, for 2 variables to be directly proportional, they must produce a graph that goes through the origin and is a straight line. Now, if we link back to the graph that we just drew, we know that this is in fact the case for the spring. So if the spring created a straight line on a force extension graph, which also went through the origin, it's going to be creating this directly proportional graph between force and extension, showing that it is obeying Hooke's law up to this maximum force of 10 newtons that we applied. So in order to get the marks here, I'm simply going to write that the line is straight. It's going to get us the first mark. So any curve in the line would mean that the 2 variables aren't directly proportional. And then in order to get the second mark, we just need to state that it also passes through the origin, so the point 0, 0, which we can see on our graph that it in fact does. And these are the 2 criteria to basically for 2 variables to be directly proportional to one another. This first part of the question should only be assessed on the higher tier paper, not the foundation one, but we're going to have a look through it anyway and just see how exactly we would go about answering it. So here we're told that we have P waves and S waves, and they're 2 types of seismic wave which are caused by earthquakes. And we're asked which one of the statements about P waves and S waves is correct, and to tick one of the boxes here. So we're going to tick one box and gain 1 mark for ticking the correct box. So if I just read through them to start with, we have that both of them are transverse, both of them are longitudinal, and then we have either that P waves are transverse and S waves are longitudinal, or the other way around, so P waves are longitudinal and S waves are transverse. So this is kind of quite a information recall type question. We're just looking to remember which type of wave the P and S waves are. An easy way that I like to do this is I remember that S waves, so transverse has an S, well actually it has 2 S's in it, and that reminds me that S waves are going to be transverse. Also, if you draw an S on its side, a few S's, you're going to get a wave somewhat like this, and that's also how we often represent a transverse wave. So that's often how I remember that S waves are transverse. For P waves, I often remember that P and S waves are different, and that just helps remind me that P waves are going to be longitudinal. Also, the long kind of stem part of the P is long as a long straight line, and that often helps me remember that they're going to be longitudinal. So then if I look back to the question and look through my options, if I have P waves being longitudinal and S waves being transverse, I'm going to tick option 4. So here I'm told that seismometers on the Earth's surface record the vibrations caused by seismic waves. And we have figure 16, which shows the vibration recorded by a seismometer for 1 P wave. So we have figure 16 below. This is the 1 P wave, and it has a time period of 10 seconds. And we're asked to calculate the frequency of the P wave shown in figure 16. So initially here I'm thinking about the frequency. We're working with the frequency which has the unit of hertz, which is equivalent to per second. And the definition for frequency is going to be defined as the number of waves that are going to pass a fixed point. It's important that this point remains the same each second, and this per second part is also very important, and that links back to this unit we have here. So in a period of 10 seconds, we need to work out how many waves we have shown above in the diagram. So how many complete waves are shown in this diagram. So if we're starting at this point in the wave cycle, we have to trace through a complete wave and get back to the same point. And we have 1 wave here. By doing the same principle through a complete wave, we get back to this point for the second complete wave, and the third point here, and then finally finishes here. So we have 1, 2, 3, 4 complete waves to pass a fixed point in 10 seconds. So now if we want to work out the number of waves to pass a point in 1 second, which is going to be the frequency, we're going to have to scale this by a factor of 10. So if we have 4 waves is equal to 10 seconds, we divide both sides by 10. In 1 second, we're going to have 4 divided by 10. So that's going to give us an answer of 0.4. And that's going to be 0.4 waves per second. So that's going to be in the units of hertz or per second. And it's going to give us a frequency of 0.4. So in this question, I'm asked to write down the equation which is going to link the following variables, so frequency, wavelength and wave speed. The command words here are write down, and the question's worth 1 mark, so I simply need to state the equation here to get this mark. This question type is quite common at GCSE, so I always tend to go about this in a similar way. So I'm going to start by writing down the letters that can be used to represent each variable. So in this case we have frequency, which can be represented by a lowercase f, wavelength, which is lambda, and wave speed, which is lowercase v for velocity. And this often helps me remember the symbol equation for the 3 variables much more easily. So I remember that v is going to be equal to f lambda. Now I can just check this using the units, just check that they work out correctly in this sense. So velocity is measured in meters per second, and that should be equal to the units for frequency, which are hertz, which equates to a unit of per second, multiplied by the unit for wavelength, which is always going to be meters. And that is going to equal meters per second when they're multiplied together, so that checks out with the units for velocity. So then I can simply write this equation down using the exact terms I've used in the question. So velocity is equal to wavelength multiplied by frequency. And that will gain us the mark here. So here I'm told that the P wave shown in figure 16 is travelling 7,200 metres per second, and I'm asked to calculate the wavelength of the P wave. And I can see that this question is worth 3 marks, so I'm going to be looking to show all of my work in along the way to make sure I pick up all of these marks throughout the question. Now I can tell here if I'm working with the wavelength, so lambda, and the speed in which it's travelling, which is v for velocity. I'm going to be working with the equation that I've just written in the previous part of this question, which is going to be that wave speed is equal to the frequency multiplied by the wavelength, so v equals f lambda. So I can start by substituting in my values. We have the velocity up here, which is 7,200 meters per second. That's going to be equal to the frequency, which is going to be the frequency that we calculated in the previous part of the question, and came to an answer of 0.4 Hertz, multiplied by the wavelength, which is the variable we're trying to work out here. Now, in order to calculate the wavelength, we need to divide both sides by 0.4. And that's going to leave us with the wavelength is equal to 7,200 divided by 0.4. And if we put this into our calculators, this gives us an answer of 18,000, which I can substitute into the box here. Now we're already given the unit meters, so it's a good idea just to go back and check that we didn't need to do any type of conversion throughout this question. So if we look at the formula here, we had the 7,200, which was in meters per second, divided by 0.4 hertz, and an alternative unit for hertz is just per second. So then these cancel out, leaving us with a unit of meters, which is what we've got at the bottom here. So we get each of our marks for firstly substituting the values in, doing the division, and then coming to the final correct answer at the end here. So this part of the question is also going to only be assessed on the higher tier paper, but again, we're going to have a look through it and see what answer we'd come up with for this question. I'm now asked to explain why the study of seismic waves provides evidence for the structure of the Earth's core. And this question is worth 2 marks, so I'm just going to make sure that I outline 2 main points here. So seismic waves are produced by earthquakes and explosions and things like that, and it's going to produce a seismic wave set of a range of frequencies which travel out through the earth and then can be detected all over the surface using seismometers. So we can use seismometers, we can put them around the earth to take in lots of data about these seismic waves, and we can analyse all of this data and detect the waves and work out a lot more about the structure of the Earth's core. So the example that we're going to focus on here for this question is the liquid nature of the Earth's core and the fact that S waves can't travel through a liquid. And this can be picked up by detections by seismometers around the Earth, and this data can be interpreted to show that the Earth's core must be liquid, which we know and think it is, and that can be shown by the fact that S waves don't pass through the Earth's core and they're unable to pass through a liquid. So to get both of the marks here, I'm firstly going to say that S waves do not travel through liquids, S waves cannot travel through a liquid, and then I'm going to go on to say that S waves do not travel through the Earth's outer core. Here, we don't have to include the word outer, but the outer core is going to be liquid and the inner core, however, isn't going to be, so it is a good idea to just make this link here also.
Figure 6 shows an unusually shaped container. The container has 4 vertical tubes of different shape and size. Water is poured into the container up to the level shown in tube 1. Complete figure 6 to show the height of the water in tubes 2, 3 and 4. So the level shown in tube 1 is here. So with this we need to think about the properties of water, or just liquids in general. So liquids tend to spread out as much as they can. And so if the level is up to what it is in figure 1, then it would actually be up to the same level in all of the 2, 3 and 4 tubes, because this is all the same container, as you can see down here. The water is in all of this container. It's one container. It's not 4 separate containers. It just happens to have 4 different sort of bits that go off it, which are different shapes. But all liquids will spread out so that they're the same level. So if you can't get it exact, don't worry too much, as long as it's more or less in the right place. So about there, and you would shade it in. You would use a pencil for this in the exam. A, because if you realise you've got it wrong, then you can rub it out. And B, just because it'll be easier to shade. So the key thing to remember here is it doesn't matter what shape the parts of the tube are. Because it's all the same container, it's going to be at the same level throughout the container. Next, the further a swimmer dives below the surface of the sea, the greater the pressure on the swimmer. Explain why. So for this, I think the easiest way for me to explain it will be with a diagram. So I'm just going to draw a quick diagram down here. So we're going to say that this is the sea, or this blue. So now, if we have a swimmer and they're up at the top or near the top of the sea, so if this is the surface, then there's not a lot of water above them, as you can see here. If they then swim down and they're further down, they're down here, there is now more water above them, and this is the key. Over here, the swimmer doesn't have a lot of water above them, and so the weight of that water that's above them isn't a lot, whereas down here they have a lot more water above them, and so there is a greater weight of the water acting on them, and that's what's causing the pressure to increase. So the answer to the question is that the volume of water above the swimmer increases, and so the weight of the water acting on the swimmer also increases. And just to quickly break that down in terms of marks, your first mark is that the volume of water above the swimmer increases, and the second is that the weight of the water acting on the swimmer also increases, or you could say the force acting on the swimmer increases. For the final part of this question, we're told that a person swims from a depth of 0.50 metres to a depth of 1.70 metres below the surface of the sea. Density of the seawater is 1,030 kilograms per metre cubed. The gravitational field strength is 9.8 newtons per kilogram. And we need to calculate the increase in pressure on the swimmer. We should give the unit, and we can use an equation from the physics equation sheet. So the first thing that we want to do is identify the things that we need from the equation sheet. So we need an equation that has depth, density, gravitational field strength, and finally pressure. Something to note as well, in the equation that we're looking for, instead of depth it actually says height, so that means the height of the water that is above the person at this point. So the depth is the same as the height of the water above them. So just in case you were confused about that, then we're looking for height of the liquid. And if you look on your physics equation sheet, then that equation says pressure due to a column of liquid equals height of column times density of liquid times gravitational field strength. You'll also see that in the equation that I've written it down with the letters, and this here is a Greek letter. It's pronounced rho, and that's the letter that we use for density. So if we find the values and substitute them in, so first of all we said that we needed the depth. This person swims from 0.50 metres to 1.70 metres. And so we can't go straight into using the equation. First we need to find what the change in depth is, or the change in height. Change in height, or change in depth, equals the final depth, or height, so 1.70, minus the original, so 0.50. And remember, we're doing height as the height of the column, and so that means the height of the water above them. So if they get deeper, then the height gets greater because there is a greater height of water above them. So 1.70 minus 0.50 is 1.20 meters. Keep it with 3 significant figures just to keep it consistent. So now back to the equation, now that we've got that. So our height that we're going to use is 1.20 meters. Next we want the density, and that's 1030 kilograms per meter cubed. And finally we want gravitational field strength, which is 9.8 newtons per kilogram. So now all we need to do is substitute those values into our equation. So pressure equals height 1.20 meters multiplied by density 1030 kilograms per meter cubed multiplied by gravitational field strength, which is 9.8 newtons per kilogram. Putting that into your calculator will give you an answer of 12,112.8. So you can leave it at that. The mark scheme doesn't require you to round it to anything. So 12,112.8. We're also asked to give the unit. The unit of pressure is pascals, and you write that with a capital P and a lowercase a. It's very important that you get the capital P there, otherwise you won't get the mark. Or you could also write newtons per meter squared. That is another unit of pressure, and that is also a valid answer. And just another thing, we didn't have to change any of the units in this question. They were all in the standard units for each value. So you don't need to worry about doing sort of gigapascals or millipascals or anything like that. You can just leave it as pascals and you're good. Figure 7 shows the apparatus a student used to investigate the reflection of light by a plane mirror. The student drew 4 ray diagrams for each angle of incidence. The student measured the angle of reflection from each diagram. Table 2 gives the student's results. So figure 7 is on your screen now, and table 2 is on screen now. First of all, you may recognise this experiment. You may have done it already. So it's an experiment to measure the angle of incidence and the angle of reflection of a ray of light. So you may remember having a mirror here. So if you just pretend that's a mirror, and you have your angle of incidence, or your incident ray. So there's the angle of incidence and the reflected ray. And as long as you have a plane mirror, which means it's smooth and straight, then the angle of incidence will equal the angle of reflection. So angle of incidence, angle of reflection, and angle of incidence equals angle of reflection. So you may remember doing that experiment. So the first part of the question is, for each angle of incidence, the angle of reflection has a range of values. This is caused by an error. What type of error will have caused each angle of reflection to have a range of values? So this question isn't asking us to say what the error is, it's asking what type of error. And so in these questions, it's most likely to either be random error or systematic error. So random error is where the measurements differ slightly, and it's usually to do with something that happened in the experiment that made some difference, some didn't. So something that happened for some measurements and didn't happen for others. So the measurements will differ slightly. And systematic error is when a problem causes all the measurements to change by the same amount or by the same proportion. So for instance, if you had a problem where you hadn't set some scales to be 0 when there's nothing on them, then all of your measurements would be off by, say, 10 grams. So that's a systematic error. So if we take a look at those two different definitions and see which one we think this is. So the angle of reflection has a range of values. So let's look back at this. And yeah, it has a range of values. There isn't, they're not all offset by the same amount. They just differ slightly. And so for that reason, we know that it must be a random error. And so that is our answer. Next, we should suggest what the student may have done during the investigation to cause each angle of reflection to have a range of values. So now we're not saying, oh, well, it was to do with the random error. We're saying what that random error was. So there are many answers for this, and the mark scheme actually says that any practical and valid suggestion will get you the mark. So if what you write makes sense and that would cause it, then you'll get the mark. But some examples would be misjudging the centre of the ray. Or another answer would be not placing the mirror or ray box in the same position each time, because if you started with a mirror that was straight like this and then your next measurement you had it slightly at an angle, but you're trying to measure the same angle into it, then your angles are going to differ off it because the mirror is at a different angle in the first place. So in that case, as I said, you would write not placing the mirror or ray box in the same position each time. Estimate the uncertainty in the angle of reflection when the angle of incidence is 50 degrees. Show how you determine your estimate. So you should already know how to find the uncertainty in a range of values, and if you don't, then I'll tell you now. The uncertainty is the range divided by 2. So looking back at the table, we want the uncertainty in the angle of reflection for an angle of incidence of 50 degrees. So we need the highest and the lowest from that row. The highest here is, or the largest value is 56 degrees, and the smallest is 46 degrees. So knowing that the range is the largest value minus the smallest value, our largest value is 56 degrees and our smallest is 46. And 56 minus 46 is 10 degrees. So that's the range. And now if we want the uncertainty, we'll come down here. So the range, 10 degrees divided by 2, because the uncertainty is the range over 2. And that will give us an uncertainty of 5 degrees. Uncertainties always have this plus minus at the start because it could be above 5 degrees or below 5 degrees of the actual value. And so we'll just write 5 degrees. If it didn't already have the plus minus written in the answer box, then you may have to put it, or you could lose marks, but in this case it's there, so we don't need to worry about it. The student concluded that for a plane mirror, the angle of incidence is equal to the angle of reflection. Explain whether you agree with this conclusion. Use examples from the results in Table 2 in your answer. So looking back at Table 2, there's actually 2 ways we could take this. So I'm going to do the way that I think I would notice first, but then I will go through the other way as well. So we want to know whether we agree with the fact that the angle of incidence is equal to the angle of reflection. So let's look first at 20 degrees. Looking at this, I would say that the angle of reflection is usually more or less equal to the angle of incidence, and so I would agree with the student because we have one value that's exactly the same and the rest of them are within 2 degrees, so that's the largest. That's the furthest away that any of the values are from the angle of incidence. For 30 degrees, again, we've got one that is the same as the angle of incidence for the angle of reflection, and the furthest away is again 2 degrees for both 32 degrees and 28 degrees. And for 40 degrees, again, we have one that's the same, and the furthest away is 3 degrees. So with that evidence, we can go back to the question and we can say the values for angles of incidence and reflection are the same within experimental accuracy. So that's basically saying that we're giving them a bit of leeway because it was an experiment and some things can go a bit wrong, like with the random error. So that would be your first mark, and your second mark would be using examples from table 2 as we're told to. And so you would say for 20 degrees, 30 degrees and 40 degrees, at least one value is the same. Or you could say that the maximum distance away that the angle of reflection is to the angle of incidence is 2 degrees or 3 degrees, which isn't much. However, there is another way that you could take this question. You could actually disagree with the student instead. Looking back at table 2, if we take a look at 50 degrees, then there is actually quite a lot of variance. We get up to 6 degrees away from the angle of incidence, and none of the values for the angle of reflection are equal to the angle of incidence. So you could instead say that they're usually different, and your example would be that at 50 degrees there are big differences, up to 6 degrees. What extra evidence could be collected to support the student's conclusion? So we want to support the conclusion that the angles of incidence and the angles of reflection are usually the same. The best way to do this, we need to gather more evidence, and so we're going to want to measure more different angles of incidence. So measure ones for 60 degrees, 70 degrees, 80 degrees, ones that we haven't measured yet. Make sure you don't just say measure again, because we don't want to re-measure the angles that we've already done. We've already measured them 4 times, and that's enough. We want to measure different angles of incidence. And finally, state one change the student should make to the apparatus if he wants to use the same method to investigate diffuse reflection. If you didn't know, diffuse reflection is when the ray of light can be reflected at lots of different angles, so it's off a rough surface. So if you had a surface that was rough and you had your angle of incidence coming in here, then because it's rough, you don't know quite where it's going to go. It could go in any of these directions. So that's what diffuse reflection is. So all we're going to do for that is we're going to replace the mirror, because that's a plane reflective surface, and so it's all one plane, it's smooth. We're going to replace the mirror with an irregular reflecting surface. Figure 8 shows a boat floating on the sea. The boat is stationary. Figure 9 shows part of the free body diagram for the boat. Complete the free body diagram for the boat. So figure 8 is there, and this is figure 9. So a free body diagram is usually you take the object and then you draw on all the forces that are acting on that object in the specific situation that you're given. So at the moment we've only got one force acting on it. We're told that we've already got the weight. However, there is more than just the weight, and that's why we need to complete the diagram. Moving back up here, the important part of this is that we're told that the boat is stationary. This is very important because it means that we're going to use Newton's first law. Newton's first law states that if there is no resultant force acting on an object, it will remain stationary or moving at a constant velocity. So the fact that the boat is stationary means that there is no resultant force on the boat at the moment. We've already got that the weight is acting on the boat, so there must be an equal and opposite force acting on the boat in order to counteract the weight so that the boat remains stationary. So equal and opposite, so it's going to be going upwards. In the exam you would use a ruler to measure out the exact length of the arrow given for the weight, but because this is on a screen it's difficult to do that, so I'm going to have to eyeball it and also use a ruler to make it a straight line. So you would draw an arrow going up. It's the same size as the weight, but now you also need to label it. Don't forget to label it in a free body diagram. We've seen that the weight has a label, and this arrow, it's for a boat floating on the sea, so it's floating on water, and the force that acts against the weight when you're on water is called upthrust, so you would label this as upthrust. There aren't any forces acting to the left or the right of the boat or in any other direction other than down for the weight and up for the up thrust. At least not that we're told about. And if you're not told about a force and you don't need to balance it out with another force, then you can just leave it. So we've got no resultant force acting on the boat now, and therefore we're done. Next, we're asked to calculate the mass of the boat. We should use the information given in figure 9, and we should know that gravitational field strength is 9.8 newtons per kilogram. Give your answer to two significant figures. Looking back at figure 9, we're actually given a scale for the diagram down here. And that's what's going to be important for this question. So we're told that 1 centimetre equals 5 kilonewtons of force. Newtons are the units of force, and kilo means 1,000. So 5 kilonewtons is 5,000 newtons. So in this case, you again would have to measure the arrow for weight, this one here, with a ruler in the exam. However, again, this is on a screen, so I'm just going to tell you how long it is. This is from there to there, 5 centimetres. So we've got 1 centimetre equals 5 kilonewtons. Back to the question. If it's 5 centimetres, and we're told that 1 centimetre equals 5 kilonewtons, then 5 centimetres equals 5 times 5 kilonewtons, which is 25 kilonewtons. Because 1 centimetre is 5, and we've got 5 lots of 1 centimetre. So now we know that the weight of the boat is 25 kilonewtons. We also know that kilo means 1,000. So therefore 25 kilonewtons equals 25,000 newtons. So 25 times 1,000 newtons. So next we're looking for the mass of the boat, not the weight. So people can get confused between mass and weight because away from physics they can be used interchangeably sometimes in just day-to-day life, but they are different. Weight is a force and it's measured in newtons, and mass is measured in kilograms. Your mass doesn't change depending on what planet you're on, for instance, whereas if you went to Jupiter has more gravity, and so you would have a greater weight because weight is a force and the force equals mass times acceleration. So weight equals mass times gravity, because gravity is the acceleration. This is the really important part. So you may know F equals ma from Newton's second law, and to get weight, you may already know that weight is mass times gravity, but just this is why. Weight is a force, so you can substitute weight in for force. Then mass doesn't change, it's just mass, and gravity is actually acceleration. So newtons per kilogram, another way of writing that is meters per second squared, which is the units of acceleration. So you can treat gravity as acceleration. So we're using weight equals mass times gravity. W equals mg. However, we want the mass, not the weight, so we can rearrange that to give us mass equals weight divided by gravity, because we've divided both sides by gravity. And then substituting our values in. So first of all, we want the weight, and that's 25,000 newtons. You need to make sure you use 25,000 and not 25. 25 kilonewtons. You never use prefixes in your calculations apart from for mass. That's the other confusing thing. So the standard unit for mass is kilograms, not grams. But for everything else, if you have kilonewtons, you need to convert it to newtons. So we're going to use 25,000. And our other value that we need is gravity, which we're given in the question, 9.8. Putting that into your calculator will give you an answer of 2,551, and you'll have a decimal, but you don't need to write that. However, we are asked to give our answer to two significant figures. So we would round that to 2,600 because our second significant figure is the 5 here. Third is this 5, and because that's 5 or above, we round up to 6, so 2,600. And that is the mass, 2,600 kilograms. And as I said, the standard unit for mass is kilograms, so we don't need to worry about converting it into any other units. When the boat propeller pushes water backwards, the boat moves forwards. The force on the water causes an equal and opposite force to act on the boat. Which law is this an example of? So straight away I'll give you that this is one of Newton's laws, and you need to know all three of Newton's laws of motion, because in this sort of question, if it's a law and it's to do with moving, you're probably looking for one of Newton's laws of motion. So we have already mentioned Newton's first and second laws in this video, however, I'll go through them again. Newton's first law is that if there is no resultant force acting on an object, then it will remain stationary or moving at a constant velocity. Newton's second law is that the force acting on an object is equal to the mass multiplied by the acceleration, so F equals ma. And Newton's third law, which we haven't mentioned yet, is that every action has an equal and opposite reaction. So looking back at the question, we need to figure out which of these laws is applying here. So the boat propeller pushes water backwards and the boat moves forwards. The force on the water causes an equal and opposite force to act on the boat. So the boat is acting on the water, and therefore the water is giving an equal and opposite force that's acting on the boat. So that applies in Newton's third law. Every action has an equal and opposite reaction. And so we would write Newton's third law. And that's the answer. Figure 10 shows the boat towing a small dinghy. The tension force in the tow rope causes a horizontal force forwards and a vertical force upwards on the dinghy. Horizontal force forwards equals 150 newtons and the vertical force upwards equals 50 newtons. Figure 11 shows a grid. Draw a vector diagram to determine the magnitude of the tension force in the tow rope and the direction of the force this causes on the dinghy. So when we're told that we should be drawing a vector diagram to determine the magnitude, first of all, and the direction, we know that we will be drawing an arrow to show the vertical force. So say we're told that it's upwards, so the vertical force, and another arrow for the horizontal force, and we will be connecting those arrows together. And the length of the hypotenuse, so this is a right angled triangle, the length of this side here will give us the magnitude of the force. We could also use Pythagoras, so if we had A, B and C, then we've got A squared add B squared equals C squared. However, in this case, they're most likely to be wanting you to just measure how long it is with a ruler. So I've got figure 11 on screen now. If you remember from the question, we were told that the horizontal force acting on the dinghy is 150 newtons and the vertical force is 50 newtons. The horizontal force was going to the left and the vertical was going upwards. So I've just written that down so we've got it next to the figure. So the first thing we need to do is decide on a scale. Looking at the graph paper that we've got in figure 11, we've got three different sets of squares. We've got the little tiny ones, we've got slightly larger ones, and we've got these big ones. For ease of understanding, I'm just going to refer to them as small, medium, and large. So, having looked at figure 11 and looked at the values, I think the best scale that we should do would be if two big squares, so two of these ones, is worth 50 newtons. So I'll just draw it down here as well, just so we remember. So first of all, let's draw the vertical component, which is 50 newtons, and we've just established that 2 big squares is 50 newtons. So we can draw that down here. We would use a ruler in the exam. I'm drawing on a screen, so I can't really use a ruler. But just make sure you do use a ruler in the exam to make sure it's completely straight. And next we've got that the horizontal component is 150 newtons. 150 is 50 times 3, so 3 lots of 50 newtons. 50 newtons is 2 big squares, and so 150 will be 2 big squares times 3, which is 6 big squares. So we can draw 1, 2, 3, 4, 5, 6. Again, you would use a ruler. We can just write on our values if we want, just so we're clear. So now we need to connect the vertical component and the horizontal component. So we want to make it into a triangle. It's going to be a right-angled triangle. And we're going to start here and go up to there. We can draw an arrow there as well to show that that's the force that's actually acting. That's the resultant force of these two horizontal and vertical components. The first thing that we're asked for is the magnitude of the force. So looking back at figure 11, the way we're going to find the magnitude is just to measure it with a ruler. We're measuring this force here. And I can't measure mine on screen, but the way that you would do it is you would measure how big each square is. So let's say we're measuring how big each big square is. And just for the sake of explanation, I'm going to say that this length is 2 centimeters. I don't know what it would actually be in the exam, but this is just to make things easier to explain because I can't actually measure on screen. So if we're saying that 2 centimeters is 1 big square, and we've already said that 2 big squares is worth 50 newtons. So if 2 big squares is worth 50 newtons, and we know that 1 big square is 2 centimeters, then 1 big square equals 2 centimeters, and that would be half of 50 newtons, so 25 newtons for our scale at least. And then if we want to know what 1 centimeter is, we can do 25 divided by 2, which is 12.5 newtons. So we've established that 1 centimetre is 12.5 newtons. So now all you need to do is measure this length, find out how many centimetres it is, and then you would times that, times the number of centimetres by 12.5 newtons, and that will give you the force that it represents. I hope that wasn't too confusing. It's quite difficult to explain on the screen, but for the magnitude, the Mark scheme says that you should end up with a value between 156 newtons and 160 newtons. So I'm going to go down the middle with 158 newtons. So having measured the length of the hypotenuse of the triangle, so this length, you should have got a value that when you multiply it by your scale, so we had 1 centimetre equals 12.5 newtons. And once you've done that, you should end up with something between 156 and 160 newtons. It might vary slightly, and they do give you some leeway, but any answer between 156 and 160 would have been accepted for the magnitude. The other value that we are asked for in the question is the direction of the force. So for this, we're looking for an angle above or below the horizontal. We know that the vertical component of this is acting upwards, and so we want an angle above the horizontal. So we want to find this angle here. So I'm just going to call that theta for now. So we've got some theta above the horizontal. And to do that, you just measure the angle with a protractor. Again, on the Mark scheme, it gives you a range of 18 to 20 degrees that you should be getting above the horizontal. And it's really important that you get the above the horizontal. So 19 degrees above the horizontal. The mark scheme does actually say that it would accept if you wrote, instead of from the horizontal, you put from the vertical, and so you would measure the other angle, you would measure this angle here. However, generally you would do from the horizontal, not from the vertical, unless it's specifically asking for from the vertical. So that is how you would do that question. A student used a simple transformer to investigate how the number of turns on the secondary coil affects the potential difference across the secondary coil. The student kept the potential difference across the primary coil fixed at 2 volts. Figure 12 shows the results collected by the student. Figure 12 is on your screen now. It's a graph. We have potential difference across the secondary coil in volts on the y-axis and the number of turns on the secondary coil on the x-axis. Our first question is, Figure 12 contains one anomalous result. Suggest one possible reason why this anomalous result occurred. So looking back at Figure 12, we can see that our anomalous result is over here. So, according to the line of best fit, we would expect that anomalous result to actually be up here, because for 25 turns on the line of best fit, we actually want a potential difference of 2.5 volts across the secondary coil. So clearly something has gone wrong. Either the measuring instrument's wrong or there's something in the experiment that's gone wrong, and that's what we're going to identify. So there are two possibilities. Either there were too few turns or coils on the secondary coil, and this would be a problem because, as you can see down here, the number of turns on the secondary coil is what we're changing. It's the independent variable. And the anomalous result actually occurs where we would expect it to occur here, so with maybe 21 or 22 turns on the secondary coil. So one of the possibilities is that there were actually not 25 turns on the secondary coil, there were less than that. And so that's the first possibility for an answer. However, there is another possibility. Instead, we could say that there is a reduced potential difference across the primary coil. And if you know about transformers, then just a quick diagram. You have a steel core, which is this shape, it's a solenoid, and you have your primary coil over here, some coils, and your secondary coil over here. And you have either more or less on one side and the other side, so primary, secondary. And the potential difference across the primary coil determines what the magnetic field will be like around the primary coil. And the magnetic field caused by the primary coil, or the current flowing through the primary coil, is what causes there to be a potential difference in the secondary coil. And so, if you have a reduced potential difference across the primary coil, then that will change the potential difference induced across the secondary coil. And that would be another explanation as to why we have a smaller potential difference in our anomalous result than we would expect there. So even though we are told up here that the student kept the PD across the primary coil fixed at 2 volts, we can say in the question that that may not have actually been the case and it was reduced instead. But you must make sure you say reduced and not just changed, because increasing it will increase the potential difference across the secondary coil, and that's not what happened in the anomalous result, and so that's not a valid explanation for it. Next, the transformer changes from being a step down to a step up transformer. How can you tell from figure 12 that this happens? So if we look back at figure 12, which is on your screen again now, you will see that the potential difference across the secondary coil moves from being 1 volt and it increases to eventually being 3 volts. Now you may remember from before, the student keeps the potential difference across the primary coil fixed at 2 volts. So a step-down transformer means that the potential difference across the primary coil is greater than the potential difference across the secondary coil, and a step-up transformer means the potential difference across the primary coil is lesser than the potential difference across the secondary coil. It's always potential difference that they're talking about with step up and step down, and the current will be the opposite. So with a step up transformer, the current in the primary coil is greater than the current in the secondary coil, so the current actually decreases. But back to the potential difference. So we can see that if the primary coil is fixed at 2 volts, then we start below 2 volts with 1 volt in the secondary coil, and we end up with above 2 volts with 3 volts in the secondary coil. And so that's why it changes from being a step down to a step up transformer. Because originally it's a step down because the potential difference in the primary coil is greater than the potential difference in the secondary coil. And then eventually it moves above the potential difference in the primary coil, so that the potential difference in the primary coil is smaller than the potential difference in the secondary coil. Now you don't need to write that full explanation in the answer box. It is sufficient to just write the potential difference across the secondary coil goes above 2 volts. And that would be your answer. A spot welder is a device that uses a transformer to produce a large current to join sheets of metal together. Figure 13 shows a transformer demonstrating how a large current can heat and join 2 nails together. How does the amount of infrared radiation emitted by the nails change when the power supply is switched on? So looking at the question, we're told that when this transformer is switched on, the 2 nails will weld together. So they must melt a bit and so be heated up. If that's what happens when the power supply is switched on, they heat up and melt, then infrared radiation is heat. And so if there is more heat when the power supply is switched on, then there is more infrared radiation, and therefore the amount of infrared radiation emitted by the nails changes because it increases. It actually increases until the nails reach a constant temperature, but that's not necessary to mention in your answer. It increases is sufficient. For the final part of this question, we're asked to calculate the current from the power supply needed to provide a power output of 336 watts. We should use the data in figure 13, and we're told that the transformer is 100% efficient. So the key things that I'm thinking about when I first look at this question is that we're using a transformer, so we're going to use an equation that's specific to transformers. And we're also looking at power and current. We're already told the potential difference, because if we look back at figure 13, we do have potential difference here as well. And so it will probably also involve the potential difference, as we are told to use the data from figure 13. So the equation that we're going to use, and you should know this equation, is voltage or PD in the primary coil over voltage or PD in the secondary coil equals the number of turns in the primary coil divided by the number of turns in the secondary coil. That is one of the equations that you'll need to know that's specific to transformers. So looking back at figure 13, I'll just write the equation up here so we've got it, and then we can sub things in. So we need the potential difference in the primary coil. Do we have the potential difference in the primary coil? No, we don't. So that may be what we're finding, or it may be that this isn't an equation that we're going to use. However, I'm telling you now it is, but you may find that you write one equation down and it doesn't work because you have multiple unknowns that you can't find elsewhere. Or we don't have the potential difference in the primary coil, but that's okay. This is the primary coil, by the way, and this is the secondary coil. Secondly, we're looking for the potential difference in the secondary coil, and we do have that. I've already highlighted it. It's here, 1.75 volts. So that's good. Next, the number of turns in the primary coil. That's here, coil with 640 turns. And finally, the number of turns in the secondary coil. And that says coil with 4 turns. Looking back to the question, we can substitute those values in. So in the exam, you'll be able to flick back and forth between the diagram and the question, but I'm just going to write those values down here because it's difficult to show both at once on a video. So we had that we didn't know what the potential difference in the primary coil was. However, that's our only unknown, so we'll be able to work it out with this equation. Divided by potential difference in the secondary coil, which was 1.75 volts, equals the number of turns in the primary coil, which was 640, divided by the number of turns in the secondary coil, which was 4. So we're just going to need to do a tiny bit of rearranging to get the potential difference in the primary coil. It's not too much. All we need to do is multiply both sides by 1.75 to get potential difference in the primary coil on its own on the left. So potential difference in the primary coil equals 640 times 1.75 divided by 4. And the answer to that is 280 volts. So now we know that the potential difference in the primary coil is 280 volts. Next, we're looking for the current. So how are we going to find the current? Well, we're also told about the power. The power is 336 watts. And so if we're told about the power in the question, then we are looking for an equation that links power, current, and potential difference or voltage, because that's what we've just figured out for the primary coil. And we're looking for the current that will be put into the primary coil. So the current from the power supply is the current that they're putting into the primary coil. And that equation is power equals voltage multiplied by current, or potential difference multiplied by current. Again, this is an equation that you should know. We're looking for current, so we're going to rearrange this by dividing both sides by voltage, and then just switching them around just so we've got current at the front. So current equals power divided by voltage. And then we can, again, substitute the values in. So we had power, that was 336 watts. We're dividing it by the voltage, and if you remember that the voltage that we just found was 280 volts, or the potential difference that we just found was 280 volts in the primary coil. And putting that into your calculator will give you a value of 1.2 for the current. And that is your answer. We're given the units of current in the question, which is amps or amperes, which is written as a capital A, and so we can just put 1.2 in the answer box. So that was a 5-mark question. It was quite long and there was quite a lot to remember and a lot of remembering equations. You'll need to remember your equations for transformers specifically. So also you'll need to remember just the general electricity equations. And a really important thing with transformers that is easy to slip up on is that you need to make sure that you treat the primary coil and the secondary coil with the right numbers. So you wouldn't want to use the voltage from the secondary coil in our equation down here for the current in the primary coil, because that will give you the wrong answer because they have a different potential difference. That's the point of a transformer. The other important bit of information, which I only mentioned once at the start of the question, is that the transformer is 100% efficient. So the only reason that that's important is because we know that all of the power that's put into the primary coil will end up being in the secondary coil, and so we don't have to factor any wasted power or wasted energy into our calculations. And that is how you would do that question. A satellite is in a circular orbit around the Earth. Figure 14 shows the velocity of the satellite at 2 different positions in the orbit. Explain why the velocity of the satellite changes as it orbits the Earth. So the most important thing to note here is that the velocity of the satellite changes. Velocity is a vector quantity, and a vector quantity has both magnitude and direction. So you may have heard of vector quantities and scalar quantities. So scalars only have magnitude. So that's things like distance, speed, mass. And vectors have magnitude and they have direction. So velocity, so there is a difference between speed and velocity. Speed is just a magnitude, and so it can be 10 meters per second in any direction. The direction isn't specified. Whereas a velocity is 10 meters per second north, maybe. And so you have to have a direction with that. And other ones would be displacement. So you can have travelled a difference of 10 metres but have a displacement of 0 because you could have gone 5 metres forward and then come 5 metres back. So you've travelled 10 metres but your displacement is 0 because you're back where you started. So that's the difference between scalars and vectors, and the fact that velocity is a vector is important in this question because even though it has the same speed all the way around the orbit, its direction is changing. So as you can see on the diagram, it starts going in this direction and then by v2 it gets to this direction. And so its direction has changed, and that is due to Earth's gravity. So the answer would be gravity causes the satellite to accelerate towards Earth. So you may have seen that the gravity of the Earth is written as 9.8 newtons per kilogram or 9.8 meters per second squared because we treat it as an acceleration. And so the satellite is accelerating towards the Earth, even though it's not actually moving sort of downwards. So if this is the Earth, it's not coming down like this. It is accelerating, and that acceleration is causing the satellite to change direction. That's your second mark. That's how circular motion works. There's an acceleration towards the centre of the circle, and that is causing the object that is going in the circle to accelerate and to change direction. So even though it has the same speed, it's changing direction, and so its velocity is changing. You'll do more about circular motion at A level if you choose to take physics further. And the final point is that if the direction is changing, then the velocity is also changing. You don't need to mention that velocity is a vector quantity, but it is something that you really need to know in order to understand why that means that the velocity is changing. If we're looking at where you would get the marks for this question, it's a 3-mark question. The first is that the gravity causes the satellite to accelerate towards Earth. The second is about the acceleration causing it to change direction. And the third is that if direction is changing, then the velocity is also changing. Figure 15 shows how the length of a satellite orbit depends on the height of the satellite above the Earth's surface. Figure 15 is the graph on your screen. We have the length of the orbit in kilometres on the y-axis and the height above the Earth's surface in kilometres on the x-axis. A satellite orbits 300 kilometres above the Earth's surface at a speed of 7.73 kilometres per second. Calculate how many complete orbits of the Earth the satellite will make in 24 hours. So our first piece of key information here is that the satellite orbits 300 kilometres above the Earth's surface. This is important because we know that connects to the graph. The graph on the x-axis has the height above the Earth's surface in kilometres, and so we can use that information to find the length of the orbit on the graph. So it was 300 kilometres above the Earth's surface, so using a ruler you can draw a line that connects 300 kilometres to the graph. So it's here. And that is the point that we're going to look at. So now we need to find the y-coordinate of that point. So we can again draw another straight line using a ruler to the y-axis. And so it's this point that we want. That will tell us the length of the orbit in kilometres. So we need to look at the scale. We've got 1,000 kilometres for each large square, and so each really little square will be 100 kilometres because each large square is split into 10 smaller squares, or 10 little squares. So we're one little square above the large square here, so we've got 42,000 plus another 100, so 42,100 kilometres is the length of the orbit. Write that down here, length of orbit, 42,100 kilometres. Okay, brilliant. That's our first point. Next, we're told that it's orbiting at a speed of 7.73 kilometers per second. And with that, we can find the time that it takes to do each orbit, to do one orbit. So we'll need another equation. We need an equation that links distance, speed, and time. And this is one of the first equations that you'll learn in science and maths. Distance equals speed times time. We want to find the time, so we need to rearrange this equation to give us time equals distance divided by speed. And we've done that by dividing both sides by speed and then just flipping them round. So we've got time on the left just because it looks neater that way. And we can substitute the values in. So first of all, distance. So we know that we want the length of the orbit for the distance. So that's 42,100 kilometres. And secondly, we want the speed. And I've already highlighted that up here, 7.73 kilometres per second. Now you may be thinking, well, they're not in the right standard units for distance and speed. However, because they're both multiplied by 1,000 essentially, because it's kilometres and kilometres per second, so they're the values that we would have if we had metres and metres per second, which are the standard units, both multiplied by 1,000. They're both multiplied by the same factor, so it doesn't actually matter. It's a division, so it's just going to cancel out. So you can convert them into metres and metres per second if you're worried about it and you're not sure, as a sort of fail-safe, but you don't need to in this case. They're both to the same factor, and so it doesn't matter. But just to show you, then you would have 42,100 times 1,000 metres divided by 7.73 times 1,000 metres per second, and then your thousands will cancel out. So that's why you don't need to worry about the units. And to get the time in seconds, if you put into your calculator, is 5,446.31 seconds. It's actually quite a long decimal, but we can just leave it there. But that's not our answer, because we're not looking for the time that it takes to complete an orbit. We're looking for the number of complete orbits in 24 hours. So we have the time that it takes for one orbit, and we want to know how many that it could do in 24 hours. So essentially, how many lots of that time will fit into 24 hours. Our time is in seconds, whereas we're looking at 24 hours. So we're going to convert the 24 hours into seconds first. So 24 hours equals, well, there's 60 minutes in an hour and 60 seconds in a minute. So we'll do 24 times 60 will give us the number of minutes in 24 hours. Times 60 again is the number of seconds in 24 hours. And that is 86,400 seconds. And then all we're going to do is divide that by the answer that we got for one complete orbit, 5,446. You would use the answer button on your calculator so you could get the exact value. Because you shouldn't round during a question, you should only round at the end. And that gives an answer of 15.86 orbits. However, we're looking for the number of complete orbits. So even though it's 15.86, so with an 8, you would usually round up to the next number. We want the number of complete orbits, and that orbit is not complete. They've done a fraction of an orbit. And so we're rounding down to 15 orbits. Because that's the number that we've completed. They haven't completed the 0.86 of the orbit, so they haven't quite completed their 16th orbit. And therefore, the answer is 15. It might have seemed like a lot. It was a 5-mark question. There was a lot going on with it. Just try and break it down, especially when you've got a graph. There will be something to do with the graph that you need to find. So look at the y-axis, look at the x-axis, look at what they represent, see if there's anything in the question that links to that, and then therefore what you can find from that value. So we found that we managed to find the length of the orbit because we knew the height above the Earth's surface. And from there, you can think about the equations that you know and what values you're going to need in order to find your answer eventually. There are two more parts to this question, so let's have a look at them. In 1772, an astronomer called J. Bode developed an equation to predict the orbital radii of the planets around the Sun. Table 3 shows Bode's predicted orbital radii and the actual orbital radii for the planets that were known in 1772. So you can see Table 3 on screen. The predicted data can be considered to be accurate. Give the reason why. We're looking at Table 3. We have the values that Bode predicted for the radius of each planet's orbit, and we have their actual radius once they managed to measure it. Looking at these values, if we first look at Mercury, the predicted value was 60 and the actual value was 58. They're pretty close. Again, with Venus, predicted value was 105, actual value 108. That's again pretty close. And this pattern continues. For Earth, 150, that was exactly 150, so obviously very close if it's exact. Mars, 240, actual one, 228, which you may think, oh, well, that's not as close as the other ones. No, it's not as close as the other ones, but it is still close within reason, and it's still impressive to be able to predict that closely to the value. You can see all the way down the table that you wouldn't confuse any of the predicted values with any of the other values. So you wouldn't look at the predicted value for Mars and then look at the actual values and think, oh, that's actually more like Mercury. You would know, you would be able to link them up together. And so the answer that we're going to give is that the predicted data is very close to the actual data. With predictions, it's very unlikely that there will be exact predictions that are perfect, and so the fact that they were pretty close is enough for us to say that the predicted data can be considered to be accurate. Finally, J. Bode used his equation to predict the existence of a planet with an orbital radius of 2,940 million kilometres. The planet Uranus was discovered in 1781. Uranus has an orbital radius of 2,875 million kilometres. Explain why the discovery of Uranus was important. So we can see here, he predicted that there would be a planet with an orbital radius of 2,940 million kilometres. And then later they discovered Uranus, which has an orbital radius of 2,875 million kilometres. You can see that those values are very close. And so the reason that this discovery was important is because the discovery supported Bode's prediction, just like in the last question, where even though they weren't exact values for them, they were very close. This is the same, that it's not exactly right, but it's so close that it does support it anyway. And so that gave evidence that his equation was correct. So your first mark is that it supported Bode's prediction. Second mark is that it gave evidence that the equation was correct or true or accurate or however you want to phrase it. And that's the end of that question. Light is usually described as a wave. Light can also be described as a stream of particles. These are two different scientific models of light. Which statement describes a scientific model? Tick one box. So our options are that a scientific model is a small-scale version of a real object, a way of guessing what will happen, or an idea used to explain observations and data. I'll tell you the answer now. The answer is that a scientific model is an idea used to explain observations and data. If we look at the other two, the first is a small-scale version of a real object. Well, that's not a scientific model. That describes sort of a physical model that you'd have, maybe like a model sea ship or something. That's not a scientific model, that's just sort of how we would describe a model in day-to-day life. And a way of guessing what will happen, well, a model is used to explain evidence that we've already got, and it might also predict things in the future, but it's based on data that we already have, and so it's not a way of guessing what will happen. It has to be an idea used to explain observations and data that we've already gained. Why do scientists sometimes have different models, like the wave and particle models of light? Well, as we found out from the last question, a model is an idea that can be used to explain observations and data. And so the reason that scientists sometimes have more than one model for things is because sometimes there's more than one way of explaining the observations and data that we've already made. There isn't always just one answer to everything. And so our answer is there is more than one explanation supported by experimental evidence. The example that's given in the question is about the wave and particle models of light, and just for some context, you'll learn more about this at A level if you choose to take physics further. But the reason we have two models for light is because there is an experiment called Young's double slits, which shows that light has to behave like a wave, and there is another experiment called the photoelectric effect, which shows that light has to behave like a particle, or a photon is what we call particles of light. And so we have two models because we can't say that it's just a wave, because then that doesn't explain the photoelectric effect, and we can't say that it's just a particle because that doesn't explain Young's double slits. You'll learn a lot more about wave-particle duality at A level. Sometimes an old scientific model is replaced by a new model. Explain why scientists replace an old scientific model with a new model, and include an example from physics in your answer. Well, as we've said before, a scientific model is an idea based on observations and data that we've made. And so if that model is replaced, then it's going to be because we've made new observations or found new data that contradicts the model that we've got already, and so we have to come up with a new model that will explain it better. And so what we would write is, new evidence cannot be explained by the existing model. So a new model is made which can explain it. And the example that I'm going to use for this is the plum pudding model of the atom being replaced by the nuclear model of the atom. You should have heard of this and Rutherford's experiment with alpha particles being fired into gold foil. And most of the alpha particles went straight through the gold foil, but a few were repelled. And because of that, he realised that there must be a concentrated nucleus at the centre of each atom, which has a positive charge, and that's why it was repelling the positive alpha particles, but the rest of the atom must be mostly empty space. And the plum pudding model was that it was a mix of positive and negative charge together, and there wasn't empty space in the atom. So there was new evidence found that showed that the plum pudding model couldn't be correct, and so then Rutherford theorised a new model. So for that we can write, for example, the plum pudding model of the atom was replaced by the nuclear model of the atom due to Rutherford's experiments. If you didn't want to use that example, you could instead talk about the geocentric model of the solar system being replaced by the heliocentric model of the solar system. You don't need to go into detail about why the experimental evidence disproved the old theory, you just need to mention the first theory and then what theory replaced it. And in terms of marks, your first mark is that there was new evidence. The second mark is that it can't be explained by an existing model. The third is that the new model is made which can explain it. And the fourth is your example of this happening in physics. Next, some students use water waves in a ripple tank to model the behaviour of light waves. Figure 16 shows what happens to the wave fronts as they pass the boundary between deep water and shallower water. Explain why refraction happens at the boundary between the deep water and shallower water. So looking at figure 16, we can tell that it's refracting because the angle of the waves has changed. So it starts, this is the direction that it starts as going in, and then this part of the wave ends up going at an angle to it, so more in this direction. And you can also see that the wavelengths have got shorter. This happens because the waves have a slower speed in the shallower water, So the edge of the wave entering the shallow water first slows down. And while that happens, the other edge continues at the original speed, causing a change in direction. Just looking back up at figure 16, you can see that these parts are the parts that have slowed down, whilst these parts have stayed the same speed. And the way I like to think about it is if you have a car or some sort of truck or something, and this is it from above, and it's going to be going into, this is mud, so this is a smooth road and that part's mud, and so when it gets to the boundary, this wheel will be slowed down by the mud because it can't drive as fast through the mud, but this wheel will continue at the same speed, and so that will drag it round because this wheel isn't going anywhere, but this wheel is, and so it will kind of curve it round, and that's why it changes direction. That's the way that I find I can understand refraction best. And this is a 3-mark question. Your 3 marks are coming from: the wave has a slower speed in shallow water, so the edge of the wave entering the shallow water first slows down, while the other edge continues at the original speed. And the causing a change in direction doesn't actually matter in terms of the marks, but it's just good to put that in just in case. Finally, figure 17 shows the wave fronts travelling parallel to the boundary between deep water and shallower water. Explain why the wave fronts in figure 17 do not refract at the boundary. Well, for this, all we need to say is that every point on the wave enters the shallow water at the same time, and hence slows down at the same time. So, because before we had an angle, then this end of the wave was entering the shallow water before this end. However, for this, these lines are all parallel with the boundary, and so they're all entering at the same time. There isn't one part crossing the boundary before the other part. They're all just going at the same time, so they all slow down at the same time, and therefore we don't have to worry about it refracting. The circle in figure 18 represents a straight wire carrying a current. The cross shows that the current is into the plane of the paper. Complete figure 18 to show the magnetic field pattern around the wire. For this question, you're going to need to use the right-hand rule. So if I just do a quick explanation of that. If you put your right hand up in a thumbs up like I've drawn here, it's not the perfect drawing, but it serves for the explanation, then you can treat your thumb, the way your thumb is pointing, so in this case it's up, as the direction of the current, and the way the rest of your fingers are pointing, so they should be curving round like this, as the magnetic field. And so when you have just a straight wire of current and you're asked to show the field, then that will show you the direction of the magnetic field. So in this case, we're told that it's going straight into the paper. Just another point, if you're not told what the crosses mean in terms of, so like this, that always means going into the paper. And if there's a dot instead, that means out of paper. The way you can think about it is like a dart. So if a dart is going away from you, it's got its little tails that end up looking like a cross. And if it's coming towards you, which hopefully it isn't, but if it was coming towards you, then you would see the point at the front. And so that means it's coming out of the paper towards you. So in this case, we've got it going into the paper. So you're going to point your right thumb towards the paper while you have your hand in a thumbs up position. And if you do that, then the rest of your fingers should be curved around, so they're going round like this. So your thumb is going straight into the paper and the rest of your fingers are going round in a clockwise direction. So that's the direction we're going to use for our answer. So the magnetic field it'll be in circles around it. The mark scheme does say that you need at least 3 circles, so make sure you do at least 3. You don't have to worry about them being perfect circles, just more or less circular. And then we said before that our fingers were going in a clockwise direction when we pointed our thumb towards the screen or towards the paper. And so that's the direction of the arrows on the field. So you want them pointing in a clockwise direction. And that's your answer for that question. The magnetic flux density 10 centimeters from the wire is 4 microtesla. Which of the following is the same as 4 microtesla? Tick one box. We've got 4 times 10 to the minus 2 Tesla, 4 times 10 to the minus 3 Tesla, 4 times 10 to the minus 6 Tesla, or 4 times 10 to the minus 9 Tesla. So for this, you're going to need to know your prefixes for your units. So first of all, we've got micro. So we need to remember what micro is. Now, this is kind of something that you just need to know, and I'll tell you how to remember it in a minute, but micro always means 10 to the minus 6. So if you've got 4 microtesla, then that's the same as 4 times 10 to the minus 6 Tesla. Now, the way I remember all my prefixes is an acronym, and so it's thank goodness my kids can meet my new perfect friend. It seems a bit stupid, but it helped me remember them, so clearly it works. And they relate to tera, giga, mega, kilo, centi, milli, micro, nano, pico, femto. You're probably thinking, why am I going through this? It's not that relevant to the question, but it's just something that I found really useful. So you can skip this bit if you don't care, but they relate to the numbers. So tera is times 10 to the 12, giga is times 10 to the 9, mega times 10 to the 6, kilo times 10 to the 3, centi is times 10 to the minus 2. So it does seem like it skips a bit there. So from kilo, it's going up in threes, the power is, and then this just skips down to minus 2. But if you think about there are 100 centimeters in a meter, and 100 is 10 to the 2, then a centimeter is a meter times 10 to the minus 2. That's the best way of remembering it, I think. And then a millimeter is times 10 to the minus 3. And then it goes back to being, it goes down in threes, the power does. So times 10 to the minus 6, times 10 to the minus 9, times 10 to the minus 12, and times 10 to the minus 15. So that was a bit of a detour, not that relevant to the question, but I do think it's a good thing to remember. I found that acronym really useful when I was doing my GCSEs. So hopefully you'll find it useful too. But yeah, the answer to the question was that 4 microtesla is the same as 4 times 10 to the minus 6 Tesla. Figure 19 shows a simple electric motor. When there is a current in the coil rotates continuously. Explain why. So this involves the motor effect, which is where if you have a wire with a current running through it in a magnetic field, it will cause the wire to move. And it's called motor effect because motor means like moving, and it's causing the wire to move. So because there is a current running through this coil here, and there is a magnetic field running from north to south across this magnet, that will cause the coil to move. However, we know because it's a coil that the current is going in different directions depending on which side of the coil it's on. And so let's just, for the sake of explanation, pick a side. So let's say that on this side it's going this way, which means as it goes round, it will be coming the other way back through. So it's going the same way round the coil, but if you just look at it from one direction, then one of it's going in one direction, one of it's going in the other direction because it's in a coil and so it has to go round. And so that will mean that the force exerted on the current, because of the magnetic field and the fact that there's a current going through the wire, will be in opposite directions for each side. So again, just for the sake of the explanation, I'm just going to pick a random side. So let's say this side has a force going upwards, which means the other side has a force going downwards. So that is actually the first part of the answer. The sides of the coil experience a force in opposite directions. You don't need to explain why or that it's to do with the motor effect. You just need to say that they're experiencing a force in the opposite directions. If we look at it from sort of this way up, and it's going like into the paper, and we have current that way, current this way, so then say we've got a force going up here, force going down here, then it's going to rotate it round. So the moment caused by those forces will cause the coil to rotate. You can see here that we have a commutator. It's called a split ring commutator because it's split into two bits. It's got two halves to it. And so this commutator is rotating with the coil. And so every half rotation, each half of the commutator will swap from being on one side of the circuit to the other side of the circuit. And so because the coil is connected to the commutator, the current will actually switch to be going in opposite directions. And so what I'm writing for that is when the two halves of the commutator swap from one carbon brush to the other, the commutator reverses the current in the coil to keep the forces in the same direction and keep the coil rotating. So just for that last bit, which I didn't really explain before, if the coil rotates round as it is now, then if I just move these, then so you saw this side before was going towards the commutator. And so if it swapped round and we didn't swap the sides of the commutator to the different carbon brushes, then now this side would be going that way and the other side would be going this way. And that would mean that the forces were reversed. So before we had that this side was up and therefore it would now be down. And this side would be up, which means it would be rotating in the other direction, and we don't want that. And so the reason we have a split ring commutator means that the current is reversed every half rotation. And that's important because it means that the forces will continue to go in the same direction and the coil will continue to rotate in the same direction. And so that's why I wrote that last bit. And finally, just to go over the marks for that, because it's a 4-mark question. Your first mark is that the sides of the coil experience a force in the opposite directions. The second is about the moments when the force is causing the coil to rotate. The third is that the sides of the commutator swap from one carbon brush to the other. And the fourth is that reverses the current in the coil. The thing about keeping the forces in the same direction and keeping the coil rotating isn't required in the mark scheme, but again, it's a good thing to write just to make sure you've got everything in case they're being particularly picky.